We are going to look into simple capacitance problem in this module. We are going to use method of moments to solve this problem. So let's look into the problem geometry itself, and I will explain you how we can later use method of moments to solve this problem. Domain geometry is going to be a parallel plate capacitor, and it's having the x and y axis in such a manner. So the top plate is going to be at V by 2 plus volt, and the bottom plate is going to be 1 by 2 minus volt. So the top plate is going to be plus half volt, the lower plate is going to be at minus half volt, and the distance between the plates is going to be A. The top plate is going to have positive charges on it, the bottom plate is going to have the negative charges minus Q, and the width of the plate is going to be given by W. So this is going to be the 2D parallel plate capacitor problem that we are going to solve using method of moments. As you know, method of moments are normally used when the surface phenomena becomes very important. For example, in this kind of problems, it is not the bulk area which is in between the two parallel plates that is important, whereas the surface phenomena, that is the surface charges, that are going to play an important role. So that is why method of moments will be a very good tool to solve such problems. And not only that, here we have got a parallel plate, but we do not need to have a parallel plate, we can have a plate of arbitrary shape. So we are going to take any shape and we are going to see release how such a model can lead to the solution. So let us assume instead of parallel plate we are going to have a plate of arbitrary shape, and this shape is going to have various elements. So elements are going to be the ones that we are going to mark with X. So when you have such a arbitrary shape, what we are interested is we are going to find the value of the response at a distance from the source. So for any charge that is going to be on the element, you are trying to see the kind of response that is going to happen for this element. So that is going to be given by the response function, which is here going to be the Green's function. So what we will do is we will start with a distance d, which is a minimal distance from the straight line extension to that element. So for example, if you are talking about a particular element, let us say this is the element you are interested in, you are going to start talking about the distance that is going to be this. So for this particular element you are talking about this distance. So the distance is the minimal distance from the straight line extending from that element. And second thing is you are trying to find the contribution of this element to the potential at that observation point. The observation point is going to be r prime, and the point where we are looking at will be r. So that is how you are going to see what is the impact of that particular charges that are at a point r, and you are going to see the impact at an observation point at r prime. So this is going to be the integral that we are talking about. So if you have this as the zeta direction, and this is going to be the starting point and the ending point. So eta s is going to be the starting point, and zeta e is going to be the ending point. So this is the starting and this is the ending point for this element, and ln of square root of x square plus d square dx, where d is the normal distance what we are talking about for this arrangement. and when you are talking about this element, you are going to extend this line and you are going to take the normal distance. So this will become the d when you are talking about this particular element. It is going to change for each and every element, but d is the normal distance, and this is the way we compute the response function. And when you expand this, what you get is minus rho s divided by 2 pi epsilon naught 1 by 2 x ln x square plus d square minus x plus d arc tan x by d. This is going to be the value, and it is going to be integrated along the limit zeta s to zeta e. So this is going to be the starting point and ending point of it. So let me write this expression in a much more clearer form here. So what we have got is the response function is equal to minus rho s divided by 2 pi epsilon naught 1 by 2 x ln x square plus d square minus x plus d arc tan x by d under the limit zeta s to zeta e. So this is going to be the way we are computing for each of that element. So this is for one element, so you have to add up all the elements. So we are now going to do this problem using a MATLAB environment. So we are going to use the MATLAB program. We have taken this code from the classical book of Rylander, Engelstrom and Bondesen called Computational Electromagnetics, and the page number is given here. And the code is basically going to help us compute the value of the capacitance using the method of moments, and we are going to solve for this problem by giving certain input parameters. So the input parameters are going to be the separation between the plates, the width of the plates, and the number of elements we are going to choose, and certain number of elements on each of the plates, so on and so forth, and we are going to compute the value of the capacitance. So in order for us to compute the capacitance, we can write the value as the absolute value that is we are interested in. Let us say we have only one element, and if we are running the problem, what we get is the value as 16 farad. And now we are going to increase the number of elements to 2, we are doubling it, and we are seeing what is the value. We are still getting 16, so we can keep increasing the value. Let us say we go to 10, we see the value here, it is 18, so it is still not converged, the value is changing quite a bit, so we can increase the value, even double it. So we say 20 elements, and we see the value is still within 18 point something, so we can increase it to 30 and run the code and see the values increasing, but not that much faster. So if we put 50, you will see that the value is almost converging very slowly, and if we increase it to 100, so this is going to be a very high value, and you will see that the value is almost in the range of 18.5 to 18.6. So this is a classical problem, and the internal aspects of the problem are basically solving the Green's function that we have described here, and we are going to use the Green's function the way we have explained it in the expression which we have shown. So if you see, the value here is going to be given by this expression, and we are taking the value and we are putting it into the A value, which is the internal memory that we are using for computing the sigma later on once you go through each of the elements. So this loop is basically going through k elements, where k is from 1 to the length of xs itself, and once you compute all the a values, so it is going to be the global matrix, you are going to invert a. So initially what you get is a multiplied by sigma is equal to phi. Since it is a simple Poisson equation, what we get is a matrix equation which is a sigma is equal to the potential, which is the phi that we are trying to solve, and once you solve this, what you get is the value for sigma, and once you get the charge density, which is, we write it as surface charge density because we are interested in the charges that are on the surface of the parallel plate capacitor. If one side is rho s, the other side will be minus rho s, because we have plus q and minus q. And once we know that, we compute the value of the charge by taking the A inverse and multiplying it with phi, and once we know that, we multiply the value of the charge density multiplied by the h, which is the length of the element itself, and that will give us the value for the charge. Once we know the charge, we can go and compute the value of the capacitance by using the formula C equal to Q by V, and we know the V is the potential difference between the two plates. So it is going to be plus 1 by 2 and minus 1 by 2, so the difference is going to be 1, and we can compute the value of C by making the value V go to 1, so it is going to be C equal to Q itself for this problem. So that is what we are doing using this code, and the code itself is self-explanatory. It has two modules. One is the input potential function itself, where you give the domain and its domain definition, and once the domain definition is given, it calls for a subroutine, which is basically a function that gives the value of charge and sigma for a given inputs which are here. So I encourage you to take the code and test it for yourself. This is an excellent example from the classical book of Rylander, Engelstrom and Bordesen, and the source of the code, as I said before, is given at the bottom of the code itself, and the page references are given here. So I urge you to simulate such problems from classical textbooks, so that you can understand very much the basics of simulation on one hand, and the other hand you can also understand how one can model such physical problems in a computational environment like MATLAB. Thank you.